Here's the definition. A function, capital F, is an antiderivative of lowercase f on an interval I if the following is true. If capital F prime of x is equal to lowercase f. For all x in that interval, for all x in I. And the math books will use epsilon to say element of. Okay. Let me put it in English, and then I'll write the math notation. For all x in I. In math symbols, we would say for all x element I. You don't have to write it one way or the other. Just want you to be able to read that. Okay. So first example. So if lowercase f of x is equal to 3x squared, then capital F is equal to x cubed. Since, by definition, the derivative of capital F, which is equal to d dx of capital F, which is equal to, just to get used to our notation again, d dx of x cubed. That simply means, whenever you see this, by the way, I don't know if it's been a while or not, but this means take the derivative of this with respect to x, right? You guys remember? I'll post the video at the end as soon as I finish uploading it. So then this becomes 3x squared, right? Doing our power rule. You guys remember the first derivative, right? Derivative rule. Are you cool with this example? I guess that's what I'm asking.
Yes, sir.
Yeah, I'm starting to understand it. Yeah. It's been a while.
Gotcha. Okay. Alrighty then. Let's keep on going. The thing I do want you to notice, though, is that this solution, there's more than one, right? Because technically, it can have a set of solutions. For example, so notice, there are other possible functions that makes this true. Do you agree that this guy would also work? For capital F, right? If I were to take the derivative of this, I still get this, right? You see what I'm saying?
Yes.
Mhm.
So this idea then becomes to become apparent that there is a family of solutions, because F2 could be something like this and still be true. You could have another one, something like that, right? No matter which one I choose, since it's a constant, I'll be good. Okay. That's the basic definition for antiderivative here. So put that in English. Since the derivative of any constant is 0, that means that f1 prime of x is equal to f2 prime, which is equal to f3, which is going to be 3x squared. Anyway, I just want to make sure that that idea is there, because it's going to come up later when you start talking about differential equations. We won't go too deep because that's a whole nother class. There's an entire class on just differential. Okay, move on.
That's derivative, right? That's what you said. It says derivative of any.
Of any constant. So any number, right? As long as it doesn't have a variable on it, derivative of that number will be 0. So stuff like 2, 5, 7, pi.
Sir, I have a question because I'm writing after you. So the f of x equal x cubed plus 1, f2 of x cubed minus 5, f3 of x cubed plus 7. Is this a 7?
Plus 7, minus 5, plus 1.
Okay, one more question. By the example, if fx equals 3x squared, then fx equal x squared, there is no sign, no dash or anything by the other f. They are the same, like if the same?
Yes, there's no derivative symbol here.
Okay, thank you.
Yeah, it doesn't start till there.
Got you.
Mm-hmm.
Thank you.
Yeah, no problem. All right, but here's the formal definition of what we're trying to say. So if f is an antiderivative of lowercase f on an interval then capital G is an antiderivative of lowercase f on I. No, sorry, let me write that better. On the interval I, if and only if, sorry, I forget that. I need to use more English, not math symbols. If and only if G is of the form G of x equal to capital F of x plus C. So they're just defining the capital F's that we talked about more formally, okay? And this would be for all x in I, where C is a constant. Okay?
We can go back and look at this right later, because
Yeah, I'm going to upload the stuff I'm writing, and I'm gonna upload the video that I'm recording right now.
okay, because they keep on flashing out with to another person using it. That's why.
I think you need to change it to. Let me see. I think you can lock
You have to,
one
if you're on
screen.
PC, you can pin the video so that it doesn't change when someone else starts making noise.
Yeah,
Okay.
should be a setting somewhere.
Thank you.
Mm-hmm.
Okay. All right. Now let's keep on going here. An example. So the question would be find a general solution of the differential equation y prime equals 2. So the question becomes, what function has
We
a
cannot
derivative?
see the.
Oh, let me screw it up then. Is that better?
Yep.
What function has a derivative equal to 2? What do you guys think?
Wouldn't it just be like x squared, or yeah, x squared?
It's close. If you take a derivative,
2x.
yeah, it's going to be 2x.
2x. Okay, my mistake.
No, that's okay. Appreciate the attempt. So the idea is that reading this theorem, right? They're asking you what is the g function, or what is the capital F? The capital F would be 2x, because if I take derivative of 2x, I end up with 2. So this is the differential, meaning a derivative has already happened. The original, y would be 2x, right? But we have to add the constant term, because we don't know what c is. So this is considered to be a general solution using theorem 1.1. So the book starts to get a little more straightforward. At first, it kind of goes a roundabout way of explaining this, which is what we're doing right now. It's trying to define every little piece. But really what we're just saying is find the antiderivative of both sides, and then you'll find the general, okay? Okay. Let's write some quick notation notes. Notation for antiderivatives. Since dy dx is equal to, well, actually, let's write an extra step. That'd be better. We know that y prime is usually equal to dy dx. This notation is better because we know exactly with respect to what variable. Y prime, we don't really know, we have to assume, unless they give us the function. So dy dx is equal to some lowercase f of x. That also implies then the following is true. Dy is equal to f of x dx. So you can multiply both sides by dx, and then solve for y in a way. That's what we're going to do. Okay. So basically, maybe I could do it on one page, is the integral. So y would be equal to the integral of f of x dx, which is equal to capital F of x plus c. So for our example, this guy would be 2x, right? This guy would be 2. For the previous example, I mean. So read the book, that's what they're trying to say. Okay?
We're finding the perspective of x right now.
What's that?
We're just finding the x right now for the
Yeah. Yeah, basically we're just gonna find antiderivative using our techniques. It's just that the book likes to define everything very formally. Okay.
Okay.
All right. So let's go ahead and move on to some examples. So here we go. Pull out the 5, and then apply the power rule. Okay. So what is the answer going to be? It'll be 5 times. There's a 1 there. So what happens?
X squared over 2.
Yeah, it'd be x 1 plus 1 over 1 plus 1, which is, yes, 2. So then the final answer would be 5x squared over 2 plus c. Okay. Are there any questions on that so far? Share this guy here. Yeah, so the derivative rules that they assume you remember, which might not be true. Right, derivative of any constant is 0. The integral of any constant will be, or integral of 0 will be c, some number. Right. Derivative of x times any number will be just a number. This guy says if you integrate a number k to get k times x, but you have to add the c. So all these guys will be helpful to remind yourself, okay? If you forgot the derivatives, they're on the left side. Now I'll send you some prettier notes later, but I figured that'd be quicker for now. Okay. Let's get back to the problems. Okay. So another thing I need you to realize is that the integral symbol is an operation. It's also called an operator. It is considered to be, I believe the word is linear. So let me show you what I mean. So let's say you had, I don't know, 5x squared plus 7x plus 3 dx. You would just integrate or find the antiderivative, of each single piece separately, and then just write it together. So basically what I'm saying, here, is integrate 5x squared dx, and then antiderivative of this guy, antiderivative one at a time. So what is the antiderivative using the power rule of this first one?
5x cubed over 3.
Yeah, so add 1 is 3, divide by the same number, right? 2 plus 1, 2 plus 1. Plus, I'm going to show the steps because we're doing it for the first time. 1 plus 1, 1 plus 1, right? And we said this guy will just be x, but we have to add the c. Okay? So, is there any questions about what just happened so far?
No, we good.
No.
Maybe that's a little better. All right, then let's move on to solving for c. In the book. Okay, so again, this is considered to be a general solution because we don't have c. In real life, this equation, if you have an equation like this, and it represents, I don't know, heat or a mechanical object or pressure or something, then the c will be an initial condition in your experiment or whatever you're observing. So this could be like a temperature. So an initial temperature would be given, or initial pressure, then you'll do your calculations and solve for c. So you'll have a specific solution to the problem you're working on, which could be anything, right? So let's do one of those. Okay. You're given let's see. Yeah, that's fine. Given a differential equation. For now, we're not going to go too deep into what that means. All that means is it's an equation that was created by taking derivatives. So given a differential equation, so this is the derivative of some function, and an initial condition, oops, f of 2 equal to 4. Find yeah, okay, make sure. Still recording. Find the particular solution. See if they use that same word. Yeah. Okay. So basically what you have to do, start here. And remember that this is the same as dy equal to 3x squared minus 1, right? Remember how we said you can multiply the dx over? So then that means the integral of dy, or I should just say this is better, say this one. So if this is true, then y is equal to the integral of 3x squared minus 1 dx. So integrate this, what is y going to be?
Raise the paper up.
Yeah.
So y equal integral of 3x squared minus integral of 1.
Yeah, 3x squared minus 1. It's the same differential right here.
Yes, yes.
Same guy.
X cubed plus C.
Close. That'd be 3x 2 plus 1 over 2 plus 1 minus x plus c. So our answer, general solution, is x cubed minus x plus c. This is the general. Okay. So you guys okay with this step, right? We were given this differential equation. We should realize that we can separate this, take the antiderivative to find the original function. So y is your regular function. Dy dx is the derivative of this, right? That's what the notation means. Derivative dy dx means derivative of this. So given the derivative, find the original, right? That's what we're doing. I'm going to change this capital F here, change this to y. In your notes, the y, put y of 2 equals 4, just to make it easier. Okay, we'll move on to the next step, because we need to solve for c. Solving for c will give us the particular. Apparently, we only have the general. Okay, let me rewrite this again. Example 4, continued. We had y of 2 equals 4. And we had the y function equal to x cubed minus x. Okay, so we solved all this ourselves. So now solve for c given this initial condition. As I said, this could be in real life a temperature, a starting point, initial force. I don't know. It depends, right? In engineering, the more complicated the problem, the uglier these equations get. So anyway, let's keep on going here. So what does y of 2 mean? Do you guys remember this notation?
But 3x squared.
This means plug in 2, right? And set it equal to 4. So when you see this in the book and in your homework, they're saying when I plug in 2 into every single x,
Every x is 2.
and the solution when that happens is 4. That's what y of 2 equal to 4 means. So don't let that bug you. Basically what they're saying is this right here means x is 2 and y is 4. That's what that means. Okay. So then solve for c, and you have the particular. So this will be 8 minus 2. That will be 6 plus c equals 4. C will be negative 2. So particular solution is y equal to x squared, cubed minus x minus 2. So this is what they wanted. So that is one particular solution. So let me show you something real quick. So again, this idea right now is about differential equations, which is an entire class in itself. So we're not going to spend too much time on this. We're just introducing the idea. So you'll see this again if you're going beyond, if you're going to engineering stuff or math major or physics major. Maybe computer science, I don't remember. All right, so can you see my graphing calculator? Okay, so the original was this guy, right? We just don't know what the heck C was. So the one we found, given those conditions, was -2. Now, since it's a family, it could be 1, could be 0, could be +1. All of this depends. So this is the family right here. So the original f, right, or y, sorry, function is something plus c, right? X cubed minus x plus c. So the c can vary depending on the initial condition. The way my math teacher explained it way back in the day, he said, you have a general and you have a bunch of currents in a lake or a river, right? You drop a rock or let's say a boat, little tiny paper boat in the river. Depending where you place it, it'll take a different path. That path will be determined by your initial condition, meaning your starting point or temperature or whatever. So the function changes, okay? That's why the C is important, and that's why my teacher would take points away when I forgot to write the C, because it's a big deal. Without the C, you don't have all solutions. Does that make sense, what we're doing?
Sure.
Yes.
Okay. Let's see here. No, we're still good.
All right.
The recording part. So in algebra, when you can move a variable up to the top or the bottom, and the only thing you need to do is change the sign of the power. So for example, you move it to the top, but it changes to -3. Okay. So now just apply the power rule. So you're gonna add 1 and divide by the same thing. So that will be, once you take the integral, you no longer write the symbol. Meaning once I start adding the number, I don't write it anymore. Okay. So that will be -3 plus 1 over -3 plus 1, which will be -1/2 x -2. But we still have to deal with that negative exponent. So you can bring it to the bottom. You can write it this way if you want. So 1 over x squared. Just like when I started, I brought this to the top. I can bring it back down. Okay. Any questions about that algebra rule?
No.
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 Do another weird one then. Let me know later if you think of something. So it's the square root of x. At first glance, it doesn't look like the power rule, but it is, right? So what power is the square root?
1/2, 1/2.
Yeah, so change it to 1/2 power. And then do the rule. So that will be x 1/2 plus 1 over 1/2 plus 1. So that will give us, what's half plus 1?
1.5.
Yeah, which is 3 halves, right? So final answer will be, when you divide by fraction, that'll be 2/3 x 3 halves.
And then we would need to, do we need to find C?
Only if they ask for a particular solution. And they have to
So-
give you initial condition.
Okay, but this is not the antiderivative, right?
Yeah, we found the antiderivative, so this is a general solution. We just
Okay.
are not finding the particular. I decided to do some more basic problems real quick, just in case these come up in the homework and they're confusing.
All right, so writing the square root of x as x to the power of 1/2 was rewriting before finding the antiderivative.
Right.
Okay, cool.
Same thing with x cubed down here. Rewrite it. Okay, 2 sin x dx. Pull out 2, and then use the formula I gave you. What is the antiderivative of sin x?
Cos x,
Is it positive or negative?
negative.
This would be 2 times negative cosine x plus c. So this is negative 2 cosine x plus c. So this one wasn't a big rewrite, but I had to factor out the 2 so you can apply the formula to this guy. This is the next one. It's 3 over x, so you need to pull out the 3. Now using your formula, excuse me, formula sheet, the antiderivative of 1 over x is going to be ln x. So this is something you need to just remember. It'll be 3 ln x plus c.
Could you pull the paper up a little bit? It's not showing up on my end a little bit. All right. Thank you.
That's fine. I mean, yeah.
So it's gonna be the 3 natural log of absolute value of x.
Yes, that's the value of x. Just do one more particular solution and then we'll move on to something else. And this time I'll use different notation. Capital F of x is equal to e to the x given the initial condition of capital F of 0 equal to 3. So this is the notation that they use in the definition. So you need to find capital F, and then you need to use the initial condition, right? So remember that capital F is equal to the integral of f prime, right? Which is equal to the antiderivative, in other words. I keep using integral, but they are the same thing for now. Okay, so integral of antiderivative e to the x is going to be itself based on the formula sheet plus c. So capital F of x is equal to e to the x plus c. So use the initial condition to find c. So f of 0 means plug in 0 and set it equal to 3. This u 0 would be equal to 1. Which means that c is equal to 2. Right? So final answer is x plus 2. Excuse me. You guys okay on the first section? It's pretty much it for section, the first one. 5 point something. This field right here has different names, but here they're calling it a flow field. Usually I hear directional field, but whatever. So remember how I was telling you that example earlier, how depending on the initial condition, you have different shapes, right? Different graphs. So the initial condition is like putting that little boat in the river, and it goes through that directional field. It creates that function. See what I'm saying? So you solve this, find the antiderivative, and then use this initial condition, and you'll find that specific graph. Okay, so that's just what they're doing. I just wanted you to see this picture, the field. So I'm not going to draw this. It takes forever. I forgot to unpause recording. Oh well. Properties for sums. Okay. So the sum of I equal 1 to n of k times ai. So what you can do is pull the k out, just like integrals or antiderivatives, and deal with the sum first. See what I mean?
Yes.
So that's one property. Another one. To I equals 1 to n ai plus or minus bi is equal to the sum of I equals 1 to n of ai plus or minus the sum of I equals 1 to n of bi. So you can separate and do the sum separately. Okay, just like antiderivatives. Just some formulas. So the sum of I equals 1 to n of some constant will be equal to c times a constant. Save you some time. I equals 1 to n of I is equal to n times n plus 1 over 2. So you don't, if you have just one variable there, you can just jump to this answer. Cool. I equals 1 to n. So I squared is another formula. We just put in n times n plus 1, 2n plus 1. Now for cubed. That will be n squared times n plus 1 squared over 4. These will be very helpful when you get to your homework. They're going to give you all kinds of weirdness, and you have to simplify, and you can just jump to the answer. Okay? Because you don't, if, for example, if I had told you this was I to 50, you're not going to do this 50 times, right? That would be stupid. Just plug in the 50 here, and you'd be done. You see what I mean?
Mhm.
If that was 1 to 50, you would just plug in the 50s here. Or if it was 1 to 10,000, you plug in the 10,000s. So you don't have to worry about it. Graphing calculators can technically do sums for you, but I don't think that's necessary when you have these formulas. Should be pretty easy. The hard part is sometimes trying to force one of these to appear. Because like, let's say you have a question that doesn't look like this, but doing some algebra will make it appear, then you'll be okay. So let's do something like that. Something that's a little harder. We have time, yeah. All right, let's do a couple of examples now. So the sum I equals to 1 to n I plus 1 over n squared. So currently I don't have, well, hold on a sec. Yeah, that's why I wrote this. So notice how this is an n, right? It's not an I. So that means you can pull it out. So you could just do this. You can say 1 over n squared will be dealt with later. So I equals 1 to n, so I plus 1 right here. That makes sense? Now apply your formula to these guys right here, these two parts. So remember, we said we can separate the sums using this property, right? So I'm going to write 1 over n squared. I'm just going to put brackets. I'm going to ignore that crap altogether. Not worry about it. So I got this sum, and I have this sum. Right? You guys agree with that?
Yes.
So what's this going to be using the formula?
N into n plus 1 over 2.
Yeah, so this will be, we're using this formula right here, right? N times n plus 1 over 2. And this guy will be this one. So just n, right? So then just combine it and we're done. Let's see. Let's get the fraction step, okay?
Can you pull the page up?
So the financial will be this guy. You can put the 2 in on the bottom, I guess. No, the n squared. So yeah, questions like these where you kind of have to play with it. That makes sense. And you may also have infinite sums. Do you guys remember your limits?
Professor, quick question. In the last step, when we implement the rule that is I equal n plus n plus 1 over 2, why we put n plus n only? From where we get this plus n? In the
This
last
guy?
line, yes, from where we get this?
Oh, it's from this formula here. Whatever's here, you times n. We had a 1 n.
Oh, okay, got it. Got it. Okay, thank you.
All right, so let's do an infinite sum. Also, just because the sum is infinite does not mean the total sum is actually infinite. Does that make sense? That sounds weird, right? I can add something infinite number of times and get a finite number. I think that's pretty cool.
What did you write on the limit?
The limit as n goes to infinity. The sum is going from I equals to 1 to n. So the instructions would be, I forgot to write them, but find the formula for the sum and take the limit. So basically just find the sum. Okay. So sadly we have to keep writing this until we take the limit. It doesn't disappear until you do it. So this would be 6i over n squared, right? Which means we can pull out the n in front of the sum, but not in front of the limit. Actually, we can pull out the 6 to do that. So now all we have is an I. So apply the formula for I, and then we'll deal with the other stuff, and then take the limit. So we will have the limit as n goes to infinity of 6 over n squared times, formula says this will be n times n plus 1 over 2, right? Yeah, that's what that guy says up there. So combine these terms and figure out what the limit is. Distribute the n, distribute the 6. We will get 6n squared plus 6n over 2n squared. What is this limit?
Six over 2.
Yeah, 6 over 2. So the limit will be 3. So the idea, remember, you look at the highest power. The degree of the top and bottom are equal. So when the degrees are equal, you just take these numbers here. If the denominator has a bigger degree, the limit which would cause the denominator to be overpowered, which would shrink everything to 0. If the degree on top is bigger, the limit will take it to infinity. So remember, back from Cal 1, right? If the degree on top is bigger, infinite. If the degree on bottom is bigger, 0. If they are equal, like this question, you take the coefficients and divide them. That makes sense?
Yes.
Yes.
Okay, so don't forget, use the formula here, some algebra, took the limit. All right, I think we'll stop here. Let's